Hey everybody. Today we're doing an example problem involving the binomial distribution. Here's the problem we're going to tackle. I recommend pausing the video and trying this on your own before seeing my solution, if you can. A school has 20 math teachers, each of whom has a 5% probability of being absent on any given day. Assuming independence, how large a pool of substitutes must the school employ in order to always have a 98% chance that they have enough subs on any given day? Let's let x be the number of math teachers that are absent on that given day. So x is going to have a binomial distribution with parameters n equals 20, because there's 20 math teachers, and p equals 0.05, the probability that any one of them is absent on a given day. It's important to note here that the potential absences are all independent of one another, so we really do have a binomial distribution in this case. We need to find the smallest number k such that the probability that the number of absences on the day is no more than k is at least 98%. So you can think about k as that pool size for the substitute teacher pool. A bit more mathematically, sort of unpacking that probability statement, we need the least number k such that the sum of the probabilities of j absences, where j is less than or equal to k, is no more than 98%. So what we're doing here inside of that summation is finding the probability of 0 absences, 1 absence, 2 absences, etc., all the way up to k. In each case, we're evaluating the probability mass function for this binomial distribution. We're thinking about getting j successes in 20 trials. So there's 20 choose j possible orderings there. And for any possible ordering, the probability is going to be 0.05 to the j, because you have j successes, times 0.95 to the 20 minus j, because you have 20 minus j failures. We can solve this in at least two different ways. First of all, and I think more directly, we can just start plugging in values of k. K equals 0, 1, 2, 3, etc., until we finally cross that 98% threshold. Alternatively, we can use technology to do this directly using the inverse cumulative distribution function. Here's the R code that gives the first few values for the binomial distribution with parameters n equals 20 and p equals 0.05. So I'm doing p binom 0, 5, 20, 0.05 to get the probability of 0 successes, 1 success, 2 successes, etc. in this binomial distribution. When k equals 3, which is the fourth value in this vector, we're already up over 98.4%. So that's going to be the answer to this question. Here's a visualization of that cumulative distribution function. You can see that it approaches 1 very quickly. I have put the threshold that we need, 98%, here as a dotted line, and you can see that we've already crossed that for k equals 3. Now technically, the cumulative distribution function of a discrete random variable is a step function. It shouldn't have these lines actually connecting the dots, but I think this visualization is much more clear and intuitive than the more accurate one with that step function. The value k can also be computed directly with an inverse CDF that's going to return the x value needed to attain a specified cumulative probability. In R, the inverse CDF is coded using the Q binom function, where we just feed Q binom the percentile that we need, in this case 98%, 0.98, as well as the parameters of the binomial distribution. We do Q binom 0.98, 20, 0.05, and we get the value k equals 3 out directly.